Welcome to the last lecture of parameterized algorithm of this semester. This is the second lecture about the lower bounds methodologies in parameterized complexity, and this time we will be speaking about exponential time hypothesis and strong exponential time hypothesis. Good. So let's start with some pitch talk about what is it about and what is this for. So the basic assumptions that we have seen so far on parameterized complexity are the following two. The first, the most standard one is simply P naught P versus NP. We assume that non-deterministic polynomial time cannot be solved in polynomial time in general. This applies to many NP-hard problems and shows that they can be solved in polynomial time, like 3C and FSAT, vertex cover, Hamiltonian cycle, and so on and so on. All of them, under this assumption, cannot be solved in polynomial time. And during the last lecture, we have seen also another assumption that is tailored to parameterized complexity, and this assumption is that FPT is not equal to W1. We have introduced W1 hardness as hardness under parameterized reduction from the Clique problem. Then we were also looking at dominating set problem, odd set problem, and so on and so on. There are several of them, and all these problems cannot be solved in fixed parameter time under this assumption. However, these two assumptions are very, in some sense, weak and therefore not precise. So let's look at some certain problems of that we are interested in, and let's look at what we know about them. So first, vertex cover. So in exact exponential time, we can solve it in definitely in running time 2 to the n by just enumerating all possible candidate solutions. Actually, this can be very much improved to, I think, 1.2 something to the n. Also during the first lecture, we have seen a FPT algorithm for this problem with running time 2 to the power k. This was simply branching on edges, which endpoint of the edge needs to be removed. This algorithm can also be improved. We have seen 1.4 something to the k, which can be improved further on. However, meaning this algorithm, they work in exponential time, but one could imagine that there is quite a lot of complexity room between the running time polynomial that is excluded by P versus NP and running time that is singly exponential, like 2 to the n or 2 to the k. So for instance, could vertex cover be solved in running time, say 2 to the square root of n, or in parameterized setting 2 to the square root of k times some polynomial in n? So neither we understand that such an algorithm can be done, nor we can exclude the existence of such an algorithm under the sheer assumption of P not equal to NP, because simply P versus NP is a too imprecise assumption for such a conclusion. And this square root n I've put here for a reason, namely when we were talking about treewidth, we have seen that actually planar vertex cover, it can be solved in both these running times. Yeah, because this was based, the first running time was based on the fact that the treewidth of a planar graph on n vertices at most square root of n, or order of square root of n, and therefore 2 to the treewidth running time of a dynamic programming gives you this running time for planar vertex cover. While for this we use this technique called bidimensionality that gave this 2 to the square root k running time. But again, you can ask the same question: can this be improved? Is the square root of n really just an artifact of the technique that we used in these two cases, the fact that we use treewidth? Or for instance, you could do on planar graphs to the power n to 1/3, or to the power k to 1/3, even better. Yeah. So this is question number 2. And again, the assumption P versus NP will not give you an answer to this question. It will only tell you that planar vertex cover is NP hard in general, so no polynomial time algorithm. And finally, if you assume, if you look at the say Clique problem or any other W1 hard problem, well, Clique can be solved in running time n power k by brute force. And we know that under FPT not equal to W1, there is no FPT algorithm for this problem, right? However, this maybe Clique actually can be solved still not in FPT time, but in better time than n power k. Yeah, for instance, you could imagine running time like n to the square root of k or n to the log k. Yeah, this is not FPT time, even if you put here any computable function in front. However, it can be much better than n power k, right? So all these questions to answer those questions, FPD versus W1 or P versus NP, these are assumptions that are simply too imprecise. And ETH, the exponential time hypothesis, is an assumption that will enable us to answer this kind of questions. And this is an assumption that is based for this field of fine-grained complexity. So in fine-grained complexity, the goal is not just to classify the classic complexity of a problem P, NP hard or something like that, but to really understand whether, say, 2 to the n or 2 to the square root n, whether this kind of complexity is optimum for a particular problem of interest. And this fine-grained complexity, this is a field that started maybe 10 years ago, or 15, and by now it is mainstream in complexity theory to try to classify the complexity of problems better under stronger assumptions, such as ETH. And the base for the assumption of ETH is, well, similar as for P versus NP, is the complexity of the SAT problem, so the satisfiability for CNF formulas. So just to recall what this is about, so we'll be working with this problem QSAT, where Q is a parameter denoting the length of clauses. So for instance, here you've got a formula in free CNF. Yes, in general, in QCNF, the clauses will be of length Q instead of 3. So we are given a formula that is in CNF. So it is of the form that is a conjunction, yes, of disjunctions. And these disjunctions, they are called clauses. And the length of the clause is this parameter of our problem. Yeah, so this is CNF, conjunctive normal form. So given such a formula, the question is whether this formula is satisfiable. Yeah. So for instance, if you look at this this formula here, maybe I can put x to 1, so x to true, y to 0, and z to say also true. Yeah. So one true, false, true. And then what would happen is that here I would get that this is true, this is actually false, and this becomes false. So this bar over a variable means a negation of a variable. Yeah. So the first clause would be satisfied because it is satisfied by the literal x. Then in the second one, I would have 1 and 1, yeah, because not y is actually true. So actually both of these literals will satisfy this clause. Here you've got 0 and 1, so this clause is satisfied by the literal set. And finally, here you have this is false, this is true, and this is also true. So this clause is actually satisfied by both of these. So true, false, true is actually a satisfying assignment for good. So this is just to recall what is CNF SAT or QSAT. So in general, CNF SAT, without any bound on the length of the clauses, it can be solved in running time 2 to the n, right? Because I can just browse through all the possible Boolean assignments to variables and just check which of if any of them is satisfies the formula. So here n is the number of variables. I will use this convention all the time, right? So for general CNF SAT, we can do 2 to the n. However, if you know some assumption about the length of clauses, you can actually do something better. So for instance, for a free SAT problem where the clauses are of length at most 3, you can get running time something like 1.308 to the power 9. This is a famous PPSZ algorithm for Paturi, Pudlak, Sachs, and Zane. It is essentially more clever branching. Well, it is much more clever branching algorithm. It runs in better time than 2 to the n. And following similar ideas for general QSAT problem, you can also get some something better than 2 to the n. So there are algorithms with running time 2 minus some epsilon depending on q to the power n. However, the savings you can get compared to power n are getting lower and lower with q going to infinity. So yeah, so those savings are tending to 0 when q goes to infinity. Yeah. So the larger Q is, the more it is inevitable that you will browse through all the 2 to the n possible Boolean assignments. Good. So this is the state of the art. For free CNF SAT, you can do something better a bit. For QSAT, you can also do something better, but not much better when Q goes to infinity. And this state of the art is the base for these two main assumptions for fine-grained complexity: the exponential time hypothesis and the strong exponential time hypothesis. So the exponential time hypothesis simply says that for free SAT, you cannot do anything significantly better than c power n. In other words, there is a delta, a positive constant delta, such that free SAT cannot be solved in time 2 power delta n, better in time 2 power delta n. So maybe you can improve the PPSZ algorithm a bit. Maybe you can do 1.2 power n or even 1.1 power n, but there is some constant, say 1.001, such that you cannot beat this constant. Yeah, so exponential time is necessary for free SAT, right? So this is this assumption, and the second assumption is essentially assumption about this convergence, about the savings for general QSAT converging to 0 when Q is going larger and larger. So more formally, for every delta smaller than 1, so you think like 2 power delta n for delta very close to 1 being something like 1.999 to the power n. So whatever saving over 2 power n you can you think of, there is some number q such that QSAT cannot be solved with this savings. Yeah, so if I take delta so that 2 power delta is 1.999, I can get some q, say, equal to 1000, such that QSAT I cannot beat this 1.999 to the power n. Yeah, so this exactly corresponds to these savings needing to converge to the to 0 when q goes to infinity. So some notes before we go further into the details. First of all, as should be somehow expected, if you assume strong ETH, this implies ETH. We will actually not show it during the lecture, but I hope that Wojtek will be able to do it during the tutorials. So a priori, you would think that that if something is called strong ETH, it should imply ETH, and this is indeed the case. But when you look at those two statements, it's not entirely clear from the beginning that one implies the other. But it is the case, but it requires more tools that we will show later. Second, if you assume ETH, then you know that free SAT cannot be solved in time sub-exponential in the number of variables. Right? Because if there was, say, 2 power square root an algorithm for free SAT, then definitely this algorithm would work in running time 2 power delta n for any small delta you would like. Yeah, so this would contradict the statement of exponential time hypothesis. Yeah, so if you assume ETH, then you know that free SAT cannot be solved in sub-exponential time, and this statement is something that many people actually regard as the base assumption for ETH. However, the formal definition is as here, and this distinction actually makes a difference in some technical reasonings when you are doing something non-trivial with exponential time hypothesis, and we will see actually an example of this later on. But this is a base corollary of ETH that many people regard as the basic formulation of ETH. Similarly, if you assume a strong ETH, then you know that CNF SAT So CNF SAT without any restriction on the length of clauses cannot be solved in anything better than 2 to the n. Yeah, so in runtime 2 power delta n for any deltas more than 1. Yeah, because if there was such an algorithm without any restriction on the length of clauses, then I could just apply it to every constant q and get a better algorithm contradicting the statement of strong ETH. Right, and also this is an assumption that often is referred to as a strong ETH. Maybe not always, but it can also serve as a substitute of strong ETH. It's a slightly weaker substitute, but many of the results actually work under this assumption instead of the full power of strong ETH. So it is also important to have this in mind, that this is a basic corollary of strong ETH. And as I said, a compact formulation of ETH and strong ETH can be formulated as follows. So in terms of those savings, so let for Q, for Q, for a parameter Q, let delta Q be the best possible exponent in which we can solve Q SAT. Yeah, so this is the infimum of all possible constants C, such that Q SAT can be solved in running time to power delta to power Cn. Yeah. So then ETH in a compact formulation just says that the saving that this delta for parameter 3 must be positive. I cannot get arbitrarily close to 0 with the algorithm, and the formulation for strong ETH says that the delta Q's tend to 1 when Q goes to infinity. Good. So these were formulations of ETH and strong ETH. We will go further into transferring lower bounds by reductions using from these assumptions. But maybe there are questions at this point about the formulation and the statements, or if there are no questions, then put a +1 in the chat so that I know that we are on board. Okay, I think that I see enough +1s. There are not so many of us in the room anyway, so yeah. Good. So transferring lower bound by introduction. So we have now assumption of ETH, which is an assumption about hardness of some problem. Yes, it is an assumption that is definitely stronger than P versus NP, because it says not only that a SAT cannot be solved in polynomial time, but it cannot be solved even in sub-exponential time. And now we can, as usual, start with reductions and transfer by reductions this assumed hardness to other problems as well. So for instance, let's look at a standard reduction from the free set problem to the vertex cover problem. So this is a textbook reduction showing NP hardness of vertex cover, but we will analyze now what kind of hardness we get from it under the assumption of ETH. So the input of such a reduction is, as usual, a formula of free in free CNF with, say, n variables and m clauses. And we want to output some graph G depending on this formula phi, so a graph G phi, together with some budget for the vertex cover. And the rule should be that this graph has a vertex cover of size at most k, if and only if the formula is satisfiable. So this is a straightforward reduction based on a standard gadget Turing. For every variable x of my formula, I will make a variable gadget. The variable gadget consists of simply two vertices corresponding to the two possible literals of the variable in question. Yes, so x and not x. So all those edges for those variable gadgets, they will form a matching. And then for every clause, you create a triangle, a clause gadget consisting of a triangle, and the three endpoints of this triangle, the three vertices of this triangle are connected, are getting connected to the corresponding literals. Yeah. So if this was a clause x or y or not z, then I just connect the vertex of this triangle to the liter. So here you see an example for this formula we had before. Yeah. So here are the four clauses. Then I create for the free variables, I create those matchings, those edges, and then for every clause I create a triangle. Note that here I've got clauses of also clauses of length 2. And what do I do with them in the reduction? I simply copy one of the literal. So for instance, here I think of the negation of y to be copied, so and therefore two of the vertices of this triangle are connected all both to the literal, not y. Yeah, so that's the reduction. So then a simple claim is that the formula is satisfiable if and only if this graph that we have constructed here has a vertex cover of size at most n plus 2m, which is now what we will call k, the budget for the vertex cover. Yeah. So this is equivalent, so we need to show two implications. Both of them are very simple. So imagine that that phi is satisfiable. So therefore, you have some satisfying assignment. Yeah. So let me draw the satisfying assignment on this reduction. Maybe x is chosen, maybe not y is chosen, and z is chosen, which corresponds to x making it true, y making it false, and z making it true. Yeah, so I pick to my vertex cover the vertices from the variable gadget that corresponds to the literals that become true by the satisfying assignment. And now observe that if you look at the, say, clause corresponding to the triangle corresponding to this clause, yes, then you see that there are three vertices in the variable gadget that are adjacent. Yes, x, y, and not z. And if the clause was satisfied, then at least one of them will be chosen. Yeah, so in this case, x. So in order to cover all the three edges inside the closed gadget, I need to pick at least two of the vertices of this triangle, and I will pick the two that correspond that do not correspond to this literal that is left that is true. Yeah, and the idea is that out of these three edges between the closed gadget and the variable gadget, two of them will be covered by the vertices chosen inside the closed gadget, and one of them will be covered from the other side, from the side of the variable gadget. Yeah. So in this way, I manage to cover all the edges using n vertices in the variable gadgets and using two vertices per each closed gadget, so n plus 2m in total. Yeah, so this was this implication. So the other implication is essentially looking at this proof and seeing that everything is tight. Because I need, in every variable gadget, I need at least one vertex to cover the edge here, this green edge here. And in each closed gadget, I need at least two vertices to cover all the three edges of the triangle. I need to exactly take. I have tightness of budget. I need to take exactly one vertex from each variable gadget and exactly two vertices from each closed gadget. Yeah. And now this means that those vertices chosen in the variable gadgets, they form some assignment, some true assignment, some Boolean assignment to the variables of the formula, and this must be a satisfying assignment. And the reason for this is that in order for every clause, in order to cover all these three edges going outside, yes, I need to cover all three of them, and I cannot cover all three of them by picking only two vertices inside. So one of them needs to be picked from one of them needs to be covered from the variable gadget side, and this means that the clause must be satisfied. Good. So I went now through a very easy NP hardness reduction for vertex cover. So let's see what are the parameters of this reduction, meaning what does reduction actually do. So the reduction takes an instance of three sets, say with n variables and m clauses, and transforms this into an equivalence instance of vertex cover. Yes, that has has 2n plus 3m vertices. You can easily check that this is the number of vertices, n plus 6m edges. Yeah, so also linear in the size of the formula number of edges, and the budget for the vertex cover is like 2n plus m. Yeah. So ETH concerns hardness of FreeSAT sort of parameterized by the number of variables. Yeah, so we need to understand what is the size of this instance in terms of the number of variables of the original formula. So M, the number of clauses, if we are dealing with FreeSAT, is in the worst case is cubic in the number of variables, right? Because reasonable FreeSAT instances will not have more than a cubic number of clauses, right? So all in all, the number of vertices and edges in the output graph that we produce is cubic in the number of variables that we started, right? So from this, we can easily see that we get the following corollary, that I cannot have an algorithm for vertex cover that runs in time better than 2 power n plus m to the power 1 over 3. So cubic root of the size of the instance, the size of the instance of the vertex cover, because if I had such an algorithm, I could pipeline the reduction that we have seen here, yes, with an algorithm with running time like that, and get an algorithm that is sub-exponential in terms of the number of variables for FreeSAT. And this we have seen that this means that ETH fails, right? So this is already nice in the sense that we got some complexity lower bound for vertex cover, but it is not nice in the sense that there is still a large gap between what we know and what we can prove as a lower bound. Yeah, meaning we know that there is an exponential time algorithm for vertex cover, and we don't know anything better than an exponential algorithm. And we expect that getting running time to do the square root of n would be rather hard. However, if you look at this reduction here, actually, we could get a lower bound that would refute the existence of sub-exponential in terms of n plus m algorithm for vertex cover, if only we assume that in the input instance, the number of clauses is linear in the number of variables. The only stupid thing I did in the proof is just I said that in the worst case, the number of clauses is cubic, but if it was actually linear, then the same reasoning would give me that there is no sub-exponential algorithm for vertex cover under the assumption of ETH. And this indeed can be done. And this is the topic of Sparsification Lemma, so-called. So this is an important result of I think Paturi, Impagliazzo, and Zane from around 2001, that essentially informally tells you that QSAT with a linear number of clauses is as hard as general QSAT for exponential time algorithm. Yeah. So in some sense, you can reduce QSAT with an arbitrary QSAT instance to a QSAT instance that has a linear number of clauses. So this is an informal statement. The formal statement is a bit more complicated. So let's go through it now slowly. So imagine that I fix some Q. This is the number, the length of the clauses in my formula that I'm interested in, and I fix some small epsilon, a positive epsilon. Then I claim that there is a constant depending on this Q and epsilon, and the Turing reduction for QSAT that works as follows. So look at this picture. So this Turing reduction will take an instance of QSAT. So this is an instance of QSAT, and will output several instances also of QSAT. Yeah, the running time of the reduction is exponential, but very low exponential. It is roughly 2 to the epsilon n. Yeah. So observe that this epsilon we could choose as small as we like. So the running time will be something like 1.001 to the power n if we choose epsilon to be small enough. Right. So the reduction works in exponential time, but as low exponential as we like. The output is a bunch of instances of QSAT, and their number is also bounded by 2 to the epsilon n. Yeah, so there's also few of them. there could not be large because the reduction itself actually works into the epsilon n time. Yeah, and these are instances on the same variable set as the original instance. Yeah? You should think of those guys as sparsified variants of phi. Yeah, and the reduction, the soundness of the reduction is as follows: that phi is satisfiable. The original formula is satisfiable if and only if one of them is satisfiable. Yeah. So in some sense, you reduce phi to satisfiability of phi to a disjunction of satisfiability of those sparsified formulas. And finally, what we gain by this reduction is that each of those psi i's is sparse in the sense that each variable appears at most c times in the formula. So it appears in at most c clauses. So in particular, this means that m, the number of clauses in my formula psi I, say m psi I, is bounded by c times n, right? Because if every variable appears at most c times, then I cannot have more than this number of clauses. Yeah, so these formulas are sparse. Good. So in other words, but what happens by shifting this, by modifying this parameter epsilon, the reduction becomes more efficient in the sense that the time complexity and the number of output instances is getting smaller and smaller. What we pay for this is that the sparsity deteriorates. Yeah. So this constant c will actually explode to infinity as epsilon tends to 0. Yeah, so this is a trade-off between the efficiency of the reduction and the sparsity of the formulas that you get. Good. Before we go further, let me only say about the proof sketch of the sparsification lemma. We will not prove it. It's also not really that hard as far as I understand. Essentially, this is branching. There's nothing else on branching. You imagine that if you got a formula phi that is very dense, this means that you can somehow find a variable that appears very often, and then you can branch on this variable. And if you branch on a variable that appears very often, this means that a lot of other things gets reduced in the formula. So the basic idea is to do branching as long as the formula is dense, and what you end up, those psi i's are the moments where you cannot branch anymore because the formula is already sparse enough, and because the branching gives you what's it called? Good progress. The running time is low. Good. Are there any questions about sparsification?
Yeah, I have a question. Can you please repeat what does it mean that formula is dense?
This was not really said formally, but dense in here means that the number of clauses is larger than c times the number of variables. Yes. So we would like to output formulas where the number of clauses is linear in the number of variables. Yes. And if a formula, I would call it dense if this is not the case. Did I answer your question?
Yes.
Good. Are there any more questions about sparsification lemma? Maybe it's also a good time to put a +1 if you are on board. Yeah, any +1s? Okay, I see +1s. Good. Good. So let's continue. So now I will show you the following theorem. That is a corollary of the sparsification lemma, and it is the most important corollary of sparsification lemma for anything we do with ETH. So I claim that if I assume ETH, then there is no sub-exponential time algorithm for 3SAT, even when parameterized by the total size of the formula. So n plus m, the number of variables plus the number of clauses. So in other words, assuming ETH, there is an epsilon, a positive epsilon, such as 3SAT cannot be solved in time 2 power epsilon times n plus m. No. So the difference from the original formulation was that in here we had only number of variables before. Yeah. So now how do we prove this? It's actually not very hard proof. It's essentially simple pushing given all that we know and applying Sparsification Lemma properly. So from ETH, we know that there exists a constant delta such that free SAT cannot be solved in 2 power delta n time. Yeah? So now I need to, under this assumption, I need to show the statement of the theorem. So imagine that let's see be this sparsity constant when we would apply the sparsification lemma for q equal to 3 because we are working with free SAT and with parameter delta. Yes, and I will also oh, sorry. Yes, so and I will also put epsilon equal to delta divided by C+2. Actually, I think I made a mistake here. Actually, I think we need to have here delta over 2. Yes. So yeah, sorry for that. So I will put C equal to C of 3 and delta over 2. And epsilon will be equal to delta over, I think, 2 times C plus 1. Sorry for that. Good. So I want to show that that now I would like to show that free SAT cannot be solved with this epsilon. So free SAT. So I would like to get a contradiction with the supposition that free SAT can be solved in this running time, 2 power epsilon times n plus m, right? Yeah. So first, based on delta, I choose C, and then based on C, I choose this epsilon. Okay, so what can we do with a given input of free SAT? First of all, we can apply the sparsification lemma. And I apply the sparsification lemma for q equal to 3 and for epsilon equal to delta half. Yes, so in running time, 2 power delta half times n order of, I can output 2 power delta half n instances, of which all of them are sparse. Yes, in all of them, the number of clauses is at most C times the number of variables, right? So now if I'm given this many instances, yes, we can solve each of them. Yes, and then because the input formula is satisfiable if and only if one of them is satisfiable, we will get the solution. Yeah, we will solve the original problem. Yeah. So how much time does it cost us? Well, we are working now with 2 power delta half times n instances of free SAT. Yes, and each of them we can solve in this running time. Yes, supposing using our supposed algorithm for free SAT parameterized by the total size of the formula. So what will be this running time? This will be 2 power epsilon. So let me put epsilon here as delta over 2 times C plus 1. Yes, times n plus m. Yes, and n plus m is actually at most n plus C times n. Yeah. So now you see that this factor is 2 power delta half times n, and this factor, once you cancel out everything, is also 2 power delta half times n. Yeah. So we managed to solve the input instance in total time 2 power delta n, which contradicts our assumption here. Yeah. So this proof essentially boiled down to applying the sparsification lemma for the right constants and brute forcing and solving all the sparse instances that we get using our assumed very fast algorithm for free SAT parameters by the formula size. Good. So this was the proof of this assumption. And now observe that having this assumption, yeah, having this theorem, we can now reduce from free SAT Yes, but we think of free set as parameterized by the formula size. Yes, so now if we get a reduction that is linear in the total formula size, in the total size of the input formula, we get also a corresponding lower bound. So starting reductions from this theorem, yes, we get, for instance, a 2 power no sub-exponential time algorithm lower bound for vertex cover, right? Because we just look at the reduction that we already had before, and for a lot of other problems like feedback vertex set, Hamiltonian cycle, free coloring, independent set. And the only thing that you need to do, you need to look at the NP hardness reduction for the problem in question that is already in the literature. And if this reduction turns out that it has only a linear blow up of the instance size, so the output instance is linear in the size of the input formula, then obviously a sub-exponential time algorithm for the output problem would give you a sub-exponential time for free set in terms of the formula size, and this by our theorem would contradict the ETH. Good. So now you can ask, okay, this was for general problems like vertex cover, feedback vertex, Hamiltonian cycle. All of them do not have sub-exponential time algorithm under ETH. But what about planar problems? Because for planar problems, we know that I actually tend to do have a sub-exponential time algorithm. For example, this algorithm running to power square root n, yes, following from the treewidth bound. Right. So let's look at the standard NP hardness reduction for planar problems. For instance, planar free coloring. So given a planar graph, is this graph free colorable? So I will not go into the details of this reduction, but essentially what the reduction from for planar free coloring does, it takes an instance of free coloring in a general graph, for which we already know that it has no sub-exponential time algorithm under ETH. It draws it in the plane, and this, of course, can introduce some crossings of edges, for instance, like here. And then at every crossing of two edges, we introduce some gadget known as crossover gadget. That sort of passes the information through the crossing. So this is a particular graph for the reduction for planar free coloring, and the combinatorics of this graph is that this graph admits certain free colorings, and all free colorings of this crossover gadget have the following form: that the vertices that are diagonally opposite here, they need to have the same color. In every free coloring of this graph, this opposite vertices, they have the same color. So in this sense, this crossover gadget manages to transfer the information about the color of this vertex to this vertex, and it transfers the information about the color of this vertex to this vertex. So you can transfer the information through a crossing. Good. So in a nutshell, this is the reduction for planar free coloring. So now, what are the parameters of this reduction? Well, this reduction takes a graph, say with n vertices and m edges, yes, and it produces a new planar graph, G prime, where the number of vertices is, well, at most quadratic in the size of the original graph. Why? Because I've got m edges of the original graph, and for every edge of the original graph, for every pair of edges of the original graph, they may cross once. Yes, if I draw edges of straight line segments, they will cross at most once, and then I will create this gadget consisting of 13 vertices on the crossing. Yeah. So the output instance has size quadratic in the input instance. So then you can claim that under the exponential time hypothesis, there is no algorithm for planar free coloring that would be better than 2 to the square root of n. So formally, there is no algorithm running time 2 to the small o of a square root of n. Yeah, because if there was such an algorithm, you would pipeline it with this reduction here. And because here the output size is quadratic, yes, then being better than square root of this output size would mean better than order of n plus m, which would contradict the exponential time hypothesis, because we already had such a lower bound for free coloring on general graphs. Yeah. And the same applies again to, say, planar vertex cover, planar Hamiltonian cycle, planar dominating set, planar independent set, and all this host of problems on planar graphs, because all these problems, when you look at the NP hardness reductions, they work using these crossover gadgets, more or less, and each of them has this quadratic blow up of the instance size here. And quadratic blow up of the instance size means square root n in terms of lower bounds that we can infer from the ETH. Good. So observe that, for instance, for the vertex cover problem, yeah, if I do not have a sub-exponential algorithm in general graphs, sub-exponential in terms of the number of vertices, then definitely I also do not have a sub-exponential FPT algorithm, where sub-exponential I mean in terms of the parameter k, say the size of the vertex cover that I expect. Yeah, why? Because, well, k is at most n, so an algorithm with this running time actually would imply an algorithm with this running time. Yeah, this is a very naive argument, but it actually works. Yeah, and similarly, if I had a planar vertex cover algorithm with a running time to this better than square root k, then actually in terms of the exact exponential time complexity, it would give me a better algorithm than to the square root n, and this is not expected under ETH. Yeah, so using this kind of reasoning for many problems, you can immediately infer parameterized lower bounds under ETH as well. But in general, all of these tools, these reductions, are actually inherently parameterized. What we were thinking about, we are reducing SAT parameter, free SAT parameterized by the size of the formula, to the problem of interest parameterized by whatever parameter we are interested in. So, for instance, if you have a free p-time reduction from the free SAT problem to your favorite parameterized problem L, and the output parameter is bounded by some function of the input parameter, which is the size of the formula, yes, then under ETH, you can claim that L, your favorite parameterized problem, cannot be solved in running time to the small o of the inverse of my parameter blowup times a polynomial. Yeah, so you get this parameterized a lower bound for FPT algorithms. And here, the inverse is understood the usual way. So this is the function such that composing f and f inverse gives you the identity. So for instance, if the blowup is quadratic, then you get a square root k lower bound. If the blowup is 2 to the k, then you've got a log k lower bound, and so on and so on. Right. So this is a general scheme for parameterized reductions under exponential time hypothesis. We will not go further into the details of particular examples where these blowups are more exotic. I hope that Wojtek during the tutorials will give you an example for getting lower bounds of the form 2 to the parameter log parameter. So running time, say d to the d. Yeah. So for instance, recall that I think during the first lecture, we were looking at this problem closest string. So the problem closest string, you've got a bunch of strings of length n, and you've got some parameter d. And the question is whether there's a sort of a center string. So a string y that is at Hamming distance at most d from all of them. Yeah. And for this problem, there was a nice branching algorithm running time d power to the order of d times polynomial in n. And using this methodology from under exponential time hypothesis, you can show that actually this running time is tight in the sense that you cannot get anything better than to the small o of d log d. Yeah. And this is a fairly non-trivial reduction. It involves a certain blow-up of the parameter, blow-up by an inverse of the function d log d. And I hope that during the tutorials, Wojtek can show you maybe not fully this result, but some introduction to how you actually make results of this kind. Good. So now we are going to go into ETH lower bounds for Clique and other W1 hard problems, because this you can also do. However, maybe there are some questions about what I said so far. And otherwise, please put a +1. I need to. Okay, I do not see that many +1s. Okay. Okay, I think we've got enough. Good, let's continue. So ETH, lower bounds, and W1 hard problems. So one of the big results, let's say, or important results in the area of ETH is that actually you can link ETH and the assumption FPT not equal to W1, in the sense that ETH actually implies that FPT is not equal to W1. More precisely, we will show in a moment that assuming ETH, the Clique problem cannot be solved in running time that is significantly better than whatever we know. With running time f of k times n to the small o of k for any computable f. Yeah. So in other words, getting a sublinear function in the exponent of the of this polynomial vector is unlikely under ETH. This doesn't mean that you cannot get something like n power k over 2 algorithm, and actually you can. There is a very nice algorithm of Neschetschil and Poliak that solves the Clique problem in running time n power omega over 3 times k, where omega is the matrix multiplication constant. So this amounts to something like 0.7 something. Yeah, so you can get something better in terms of the multiplier in front of k, but you cannot get a sub-exponential, sublinear function of k in the exponent under ETH, even if you put in this multiplier here any computable function. And this is a little bit of magic, yeah, that we are now going to prove, because we are going to prove this theorem. We are going to prove a lower bound against any computable function. But let's not think about it for now. This will be clarified at the end, how you actually make a lower bound against any computable f. Let's, for concreteness, fix some function k, let's say 2 to the k. So now we are going to prove a lower bound excluding running time 2 power k times n to the small o of k. Yeah, so this is the lower bound that we are aiming at now. So we will reduce from the free coloring problem. So for this free coloring problem, we know that there is no sub-exponential time algorithm under the exponential time hypothesis solving free coloring in terms of the number of vertices. So the input of the reduction will be a graph G with n vertices, and our question is whether this problem can be this graph can be colored with 3 colors. Okay. So the reduction works as follows. So here is the reduction, and here is the figure for the reduction. So first of all, let me choose the parameter. I will choose k to be log n. Let me fix k to be log n. So now here is my graph G that I get on input, and now I partition the input, the vertex of the input graph into k parts, v1, v2 up to vk, each of size, well, roughly n over k, maybe n over k ceiling. Yeah, but I will ignore those ceilings in the analysis, of course. Yes, so I just arbitrarily partition the vertex. Yeah. So now I create an instance of the Clique problem that I will be solving later on using our assumed good algorithm for Clique. And the construction is pretty funny. Namely, let me look at, say, part v1, and I'm looking at every possible free colorings of the graph induced by this part. So what I'm doing, I'm browsing through every possible free colorings of those vertices. I'm checking which of them actually are valid free colorings of this graph induced by those vertices. And for each such a valid coloring, I create one vertex of my output graph G prime. So for instance, if I look at the vertex, maybe this one, this corresponds to a coloring lambda of this graph G of V1. Yes, and maybe this coloring looks like that this vertex is red, this vertex is red, maybe this vertex is green, and this vertex is blue. Yeah, so this is a possible vertex of my output graph. And similar I do for V2, for V3, and so on up to Vk. Yeah, so all these vertices of my output graph are valid free colorings of this induced subgraph. Yeah? So observe that those parts U1 up to UK that I create in this manner, how large they are. Well, UI is at most as large as the number of possible free colorings of the relevant part. So it is at most 3 to the n over k. Yeah, because there are n over k vertices in this part. Good. So now these are the vertices of my graph G prime. Now I need to declare the edges. There will be no edges within the UIs. So actually the output will be a multicolored Clique instance. How convenient. And now I need to say when I'm considering one coloring lambda here, adjacent to some other coloring, say kappa of U2. Right, so the coloring kappa of U2, this is a vertex of from U2, and this corresponds to some coloring, say this one of say the second part, and I'm making those two guys adjacent. So I'm putting an edge between this vertex and this vertex in G prime, if and only if these two colorings in my original graph G were compatible. In the sense that if I look at the parts V1 and V2 combined, at the subgraph induced by both of those parts at the same time, then actually I do not see any edge that has both endpoints of the same color. Yeah. So for instance, if the adjacencies would be like that, this would be okay because there are no two edges with endpoints of the same color. Yes. So then lambda and kappa would be adjacent in my output instance G prime. However, if there was an edge like that, then I would not put an edge between lambda and kappa because taking their union doesn't yield a proper free coloring of the subgraph. Good. So now the easy claim, however a bit magic claim, is that the original graph has a free coloring if and only if the output instance has a clique of size k. So why so? If there is a free coloring of this graph, so maybe these vertices are red, maybe some other vertices are green and so on, then what I can do, I can simply look at the vertices corresponding to the restrictions of this coloring to particular parts. These vertices exist because the colorings are consistent within each part. And also there are pairwise edges between those vertices. Yeah, because, well, if this was a valid free coloring of the original graph, then it is also valid for every particular pair of parts. Right? So this is this implication. And the other implication is that if I've got a clique here, yes, then this clique corresponds to some choice of colorings of parts. So by taking the union of those free colorings, I get a free coloring of the original graph, and I need to say why it's proper, why there are no edges with the same colors at the endpoints. Well, there cannot be edges with the same colors at the endpoints within every part because these were valid colorings of each individual part. And also there cannot be edges of the same color, say between part 3 and part 4, because then the coloring of part 3 and the coloring of part 4 together would not yield a proper coloring of those two parts combined. Yes, and I assume that I started with a clique on the right hand side. Good. So this was the proof of this claim, that free colorability of G is equivalent to the right hand side, the graph G prime having a clique of size n. Good. So now suppose that I've got a super fast algorithm, super efficient algorithm for solving my target problem, my clique problem. Yeah, so an algorithm that would run in time 2 power k times n to the small o of k. Yeah. So what is n? The total number of vertices of the output instance of the output graph G prime. Well, it is at most in each of the parts I've got 3 power n over k vertices. Yes, where n is the size of the input. Well, and there are k parts. Right. So this is the size of the number of vertices of the target graph. So now by applying this running time, yes, to an instance of this size, yes, what do we get? We get 2 power k times n to the small o of k, which is what? 2 power k times k power small o of k, right? Times what? Times 3 to n over k to the power small o of k. So let me rewrite it a little bit. So this is 2 power k, that's okay. K to the small o of k times 3 to power n times small o of k over k. Yeah. And now recall what was actually k. K was chosen to be log n. Yeah. So what is this? This is small o of log n over log n, which is small o of 1. Yes, this is a factor that converges to 0 as n goes to infinity. Yes, so all of this is 3 to small o of n. What is this? 2 power k. This is 2 power log n, yes, which is n. And k power log k, this is log n to the power small o of log n. Yeah, so this is something that is actually definitely sub-exponential. This is to the small o of n. Yeah, this is something like to the small o of log square. Yeah, so all these parts, this, and this, they're all sub-exponential in n. So this is 2 power small o of n. And we have solved the original free coloring instance in sub-exponential time. So contradiction with ETH. Okay, so why did we actually need this k to be log n? Well, for this factor. This factor was important because when you look at this factor, yes, if for instance f of k would be 2 power k, yes, then actually 2 power log n, yes, then this would be very bad, right? Because then this would not be polynomial in n, so in particular sub-exponential in n. But then we can also modify our choice of k. If we had this f of k being 2 power k, then we would simply choose k to be log k. Yeah, because then if we choose to log n. Yeah, so if we choose k to be doubly logarithmic in n, then f of k will be actually polynomial in n, and it would not spoil the fact that the whole reduction works in sub-exponential time, and the output algorithm works in sub-exponential time. So in general, how you should pick k, the number of parts that you are interested in, you should pick it to be the inverse of n. Yeah, so formally it is the maximum number I such that f of I is at most n. Yeah, so in this way, if you define k in this way, then on one hand you have this property that we used here, that k is actually a growing function of n. Yeah, so it is small o of omega of 1. So it is a very slowly growing, very slowly increasing function of n. So in particular here, I would get something something better than 2 to the n. And on the other hand, on the other hand, because it is so slowly growing, this factor f of k will actually be only bounded by n, right? So there is a caveat with this choice of k that maybe you see now, namely the reduction itself. It needs to compute k. Yeah, it needs to know into how many parts we need to divide the vertex of the original graph, right? And this was fine for our functions like log n, log n, and so on, because this inverse function of f is efficiently computable. Like a function log n can be computed in time polynomial in n, and this is good enough for us. But if we assume f to be only a computable function, yes, then it is not clear in what running time we can actually compute the inverse of f applied to n. In particular, maybe this running time is exponential in n, or even doubly exponential in n, and this would spoil the fact that the reduction plus the algorithm works in sub-exponential time, because just computing the parameter k would take say doubly exponential time. So there is a way around it. So far, our proof works for well-behaved functions f, for which the inverse is polynomial time computable. There is a way of avoiding this. It involves defining f to be slightly differently based on the number of steps in a Turing machine that computes f, and in particular, it uses the computability of f, and you can see how to solve this in the platypus. So because these are computability issues, and this involves getting your hands dirty in Turing machines, I don't want to go into this. But for this proof works for all well-behaved functions f, like say a tower of exponentials. Good. Are there any questions about this proof? Because now we are finished. Maybe some plus ones, please. I do not see that many. Okay, I see some. Maybe some questions, doubts. Maybe I can clarify something. Okay, let's just continue then. There are enough plus ones. Good. So now that we know hardness of the Clique problem under ETH, we can transfer this hardness to other problems by parameterized reductions. And we already have seen parameterized reductions, and we can analyze what they mean for the complexity of problems in question. So for instance, for the multicolored Clique instance, apart from the fact that our reduction proving hardness of Clique actually yields a multicolored Clique instance, we had a reduction from Clique to multicolored Clique that did not change the parameter at all, right? It was only copying the universe size. So therefore, I can now infer the same running time lower bound for the multicolored Clique instance, because if I had an algorithm with this running time for the multicolored Clique, then by pipelining the reduction with this algorithm for multicolored Clique, I would get a reduction. I would get an algorithm with this running time, f of k times n to the small o of k for the Clique problem, therefore refuting ETH again. Yeah. Similarly, for the dominating set problem, we've got a reduction with a linear blowup of the parameter. Actually, no blowup. It was identity function for list coloring parameter for parameters by treewidth. All these problems, whenever we've got a reduction where the parameter blowup is only linear, then you've got this kind of hardness. When you look at the reduction we had for the odd set problem, yes, this reduction was a little bit different because the original parameter k was being blown up to parameter k prime equal to, I think, k plus k choose 2 in the output instance, which is order of k square, right? So then we can claim only this kind of hardness for the odd set problem, right? Because only this kind of an algorithm for here k substituted with k prime, yes, pipeline with the reduction from Clique to odd set would give us a contradiction. So again, the parameter blow up in the reduction governs what kind of running time lower bound we get. Yeah. So let me just mention that actually this is not the state of the art for odd-set. You can do better. You can improve this hardness to hardness of the form any computable function time anything better than n power k over log k. So this is a little bit strange. Why this factor k over log k? It actually comes from some black box. However, the running time lower bounds of the form f of k times n to the small o of k are not currently known for odd-set, and for a host of other problems that suffer from a similar problem. You can actually also read in the Platypus book how you get this this running time lower bound for odd-set and for similar problems. It is by using a different black box, a different hardness source than Clique. Good. So this was some remarks about W1 hardness. And now finally, during the last 20 minutes, I would like to speak a little bit about strong ETH and hardness lower bounds that you can get from strong ETH. So recall the strong ETH is this version of ETH where you assume that as Q goes to infinity, the savings over the 2 to the n running time, brute force running time, diminish to 0 for the such problem. Yeah, so for every delta smaller than 1, there exists a Q such that Q sat cannot be solved in running time to power delta n. Good. So as I said, strong ETH implies ETH. This is a result that uses Sparsification Lemma, and hopefully this will be a good exercise to get accustomed to Sparsification Lemma. And the typical situation is that a result under the exponential time hypothesis, because the exponential time hypothesis only tells you something about the sort of asymptotics of the exponent, will tell you, say, your favorite problem Q cannot be solved in the running time sub-exponential. Yeah. A typical result under strong ETH will pinpoint the exact base of the exponent. So because strong ETH sort of pinpoints the exact base of the exponent to be 2 for Q sat as Q goes to infinity, then this can be used to pinpoint exact bases of exponents for several parameterized problems. Yeah, so a typical result would be that Q cannot be solved in running time 2 minus epsilon to the power k for some relevant parameter k times polynomial for any epsilon that is positive. Yeah, so base 2 is optimal. And we will see now one result of this kind. It is actually a very nice reduction. We will show that, recall that when we were looking at dynamic programming on bounded treewidth graphs, we had an algorithm. One of the basic ones was an algorithm for the independent set problem that was running in time 2 power t times polynomial in, where we are given a tree decomposition of width t. And now we will prove that this 2 in the base of the exponent under the assumption of a strong ETH is actually optimal. In a sense that under strong ETH, there is no algorithm that given a graph G and the tree decomposition of width t solves the independent set problem on this graph in running time 2 minus epsilon to power t for any small epsilon that you'd like. Good. So yeah, we are going to prove it, and it will be again a nice reduction. So suppose that there is such an algorithm, and we will. So from strong ETH, yeah. So there is such an algorithm for some epsilon, right? So we have some positive epsilon, and we know under the strong ETH that there is some Q, which is a constant, yes, so that Q sat cannot be solved in 2 minus epsilon to the power n. Yes, so for instance, if epsilon is such that if epsilon is say 1%, this means that there is an algorithm working for independent set in power in running time 1.99 to the power t. And now we would like from this to prove that QSAT can be solved in runtime 1.9 to the power n. Yeah, and for some Q, this is actually contradicting ETH, strong ETH. Yeah, so we will use this algorithm for the independent set problem to do this, to solve QSAT in this running. Yeah. So note that Q is a true constant, but it is chosen depending on epsilon. So what we are now trying to do, we are trying to determine the side satisfiability of a QSAT formula. So we are given a QSAT formula phi. Say it has n variables and it has m clauses. Good. So now comes the reduction. We are now computing based on this formula a graph where looking for independent sets will verify satisfiability of the formula. So the graph will look roughly like this. It will be like a long sausage composed of several paths with some stuff attached to this sausage. So for every variable x, yes, I will create a path of length 2m. Yeah. So this is the path created for the variable x1. This is a path created for the variable x2, and so on and so on and so on. Each of them has maybe not length 2m, but with 2m vertices. Yeah, it's always confusing whether length of a path is the number of edges or the number of vertices. I would like to have here that each of those paths has exactly 2m vertices. And because there are 2m vertices, they are kind of can be naturally divided into those columns that I drew here. So each consecutive column consists of 2 next vertices from each of the paths. Right? So there are m columns like that. Yes, each of them consists of 2 vertices, a pair of vertices on the path. So there are m such columns, and each of the columns is assigned to a different clause. Yeah, so for clause, say ci, the if clause, I create a clique, an additional attachment that is a clique of size equal to the size of this clause. So for instance, if this is a clause consisting of 3 literals, I create here a triangle. If I have a clause consisting of only of 2 literals, I create an edge. And now I attach this this gadget created for the clause to the corresponding path, and I do it like that. So if if I have x1 here, I take one vertex of this clique and I attach it to the left vertex of the pair. If I have x3, I also attach it to the left vertex of the on the path corresponding to x3. But if I have a negation, say negated x5, not x5, I attach it to the right vertex. Yeah. So I attach different vertices of the clique to different places on the paths. Yes, and I attach to the left vertex or the right vertex of the pair, depending on whether the literal is positive or negative. Yeah. So for instance, for this clause x3 or not x5, I would attach it to the left vertex on the x3 path and to the right vertex on the x4 path. Okay, so now what I claim about this this reduction, and this claim is not entirely true. We will fix it on the way. I claim that the formula is satisfiable if and only if the graph that I produce in this way has an independent set of size m times n plus m. Yeah, so this you should read m vertices per each path. Yeah. So m times n means that I need to pick m vertices from each path, and then I need to pick m vertices additional. Yeah. Okay, so let's see the implication that is actually true at this point of this equivalence, namely the left to right implication. That if I have a satisfying assignment, then I've got an independent set of this size in this graph. Yeah. So I will, from each of the paths, I will take m vertices to my independent set. And there are 2 natural ways of doing that. Maybe the red one will be the independent set. Either I pick the, say, the left guys from each of the pairs in columns, or I pick the right guys. Yeah. Maybe here I pick the left. And I will pick the left guys. So the left guys if the variable is false, and I will pick the right guys if the variable is true. Right? So I pick in this manner along the path, and this means that in this independent set instance, so far I picked m times n vertices because I picked m per each path. And now maybe this one will also be true. Yeah. So now I need to somehow conjure up m more vertices to my independent set, and well, I will pick them from the clause gadget. And this is a similar idea as we had already in this first reduction, that now we've got here a clique. So I need to pick at most one vertex from this clique. And I can pick one of them only if one of these attachment points is not picked so far, which exactly corresponds to the to this clause being satisfied. Yeah. So here, if I picked, if I evaluated both x1, x3, and x5 to be false, yes, then only one of these attachment points becomes is still free, is still not taken, and this gives me one possibility of taking a vertex from this clique to the independence. And because every clause is satisfied, yes, then I can, in each of those cliques, and I can pick one vertex, and I will get this many vertices in total. Right. So let's try to make the second implication, and this will fail, but it will fail in a way that we'll be able to fix. So first of all, I've got I need to pick n plus m vertices. So I need to pick m vertices from each path, yeah, because I cannot pick more than m vertices on each of the paths, yeah, because a path of length on 2m vertices does not have an independence of size m plus 1. And I need to pick one vertex from each clique, because in every clique I can pick only one vertex. And this is tightness, right? I've got this, I need to pick this many. So I need to pick m vertices from each path, and I need to pick one vertex from each clique. So then the problem is that if we had an assumption that on each of the paths, I do exactly one of these two options, I either pick always the left guys or always the right guys, then we would be happy, meaning then the assignment, then the choice on the paths would correspond to some truth assignment, true, false, depending whether you pick the left guys or the right guys. And then the clause gadgets would verify that that every clause is satisfied by the corresponding by this valuation of variables, because in every clause gadget I need to have one vertex left to be chosen, which verifies that the clause is satisfied. Yeah? But there's a problem, because now if you look at what happens is that my solution can cheat. My solution can first start with a false assignment, taking the left guys, and then make a skip. Yes, suddenly start to take the right guys, and this is still an independent set of size m on this path. Yeah. However, the valuation at this point of this variable at this point changed from false to true. Yeah. So this is a problem. And how you deal with this skipping is actually quite fun. You simply repeat the whole construction. Namely, instead of making paths of length 2m and adding one clause gadget per every clause, I just make the whole construction repeated n plus 1 times. And the funny thing is that, well, along each path, you can have at most one skip, yeah, because you can only skip from false to true. Yeah. So maybe here I will have a skip, maybe with a different color. Maybe here I will have a skip on path number 1. Maybe here you will have a skip on path number 2. Maybe here there will be a skip on path number 3. But because there are n plus 1 copies of those call constructions and only n paths, one of the copies, yes, will be entirely skip free. So in one of the copies, every path will be either picking only the left guys or only the right guys. Yes? And because in each copy we independently also reiterated the checking of the clauses, this means that whatever satisfying assignment is encoded on the paths in this copy, yes, it is verified by the clause gadgets that that this is a satisfying assignment of the formula. And of course, this means that this budget needs to be also multiplied by n plus 1. I guess that that this goes without saying, yeah, because the whole construction is repeated. Good. So I hope that with this fix, this claim is now proved. Yes. So our instance of independence that exactly encodes the satisfiability of phi. And the final touch is to observe that this graph that we have created here has treewidth n plus k, n plus q at most, which is n plus constant. And to see it, it is easy to see it using the Cops and Robber game. Essentially, you can create a tree decomposition of this graph, even a path decomposition, by taking n cops and starting them, maybe blue, and putting them first on the left of each path, and then you scan this whole graph left to right, and you have q additional cops in the rear whenever you place the cops on this attachment points. You use q additional cops to clear the clique. Good. So I hope that you can imagine that the tree of this graph is n plus q, yeah, which is n plus order of 1. And now you can easily see that if you had an algorithm with this running time for independent set, yes, then by just applying this algorithm on this tree decomposition of this graph, we could solve this instance, and by the claim also solve the input instance of q set in running time that would be like that: 2 minus epsilon to n plus q times polynomial in the input size. Yeah, and because q is a constant, this is a running time of this form. Yeah, and this would contradict strong ETH. Yeah. So observe that in this proof, actually, it was important that q was a real constant. I could not start with a general CNF SAT instance with arbitrary length of the clauses, because then I would need to create those cliques. The closed gadgets would be clique of very large size, which would blow up the tree of the graph. Yeah, you can get around it. You can actually prove the same lower bound under just the assumption that a CNF SAT cannot be solved in better time than 2 power n. You need to replace the cliques as closed gadgets with some more intricate construction that serves essentially, which has the same functionality. Good. So in the remaining 2 minutes, let me say something about further color of strong ETH, because there are many and they are actually kind of important. First of all, strong ETH can be used to prove hardness of for p-type solvable problems. So there is this important problem called orthogonal vectors. You've got 2 lists of binary vectors, say of length n. And you want to check whether you can take one vector from one list and one vector from the other list so that they are orthogonal. Yeah, so because the vectors are 0, 1, this essentially means there are no ones on the same position. So this clearly can be solved in quadratic time by just iterating through all the possible pairs. Yes, but under strong ETH, you can prove that this problem can be solved in strongly subquadratic time. So n power 2 minus epsilon. So I hope that maybe Wojtek can do this during the tutorials, and I know that Mikołaj Bojanczyk did it during the complexity theory course, so I hope that many of you have already seen this. But this is a base for many reductions for polynomial time solvable problems. So under strong ETH, you can actually proof like no subcubic algorithm nor subquadratic algorithm for problems, and this is something that is very important in fine-grained complexity nowadays. From strong ETH, you can also prove a different kind of lower bounds. For instance, for the dominating set problem, you can prove that even getting anything better than n power k brute force is unlikely under strong ETH. And you can also make strong ETH lower bounds for different parameterized problems. For instance, if you look at a heating set problem parameterized by the size of the universe, the trivial brute force is 2 power the size of the universe. And you can prove under strong ETH that you cannot get that this 2 in the base of the exponent is actually optimum. You cannot get 1.99 to the power of the size of the universe. Good, so that was it for the strong ETH. Are there any questions regarding this or the whole lecture today? Okay, if there are no more questions, then I would like to thank you for this lecture, and I would like to thank you also for this whole semester. This was a kind of an experiment how to do it in an online way, but I hope that you liked our lectures, and yeah, we see each other at the exam.